here. Are you lot looking at a copy of Cengage WebAssign right now? Okay, let's tell you what's going to happen from now, essentially to the end of the quarter. So we normally do things in 2-week stints, and we've done 8 weeks, right? And that was test 4 that's just over. So what's left? This is what's left. We have got 8.3, which we're going to do today, which is applications of integration to engineering and physics. And then chapter 9. Chapter 9 is all about differential equations. And all of this, that's 5 sections of homework, will be due on Sunday, the 6th of December. So you can tell it that's quite a long way away, right? But you got to remember Thanksgiving's in the road. I can't stress this enough. So I'm going to do my tell students it 3 times so they'll remember. If you do not do your homework as soon as you are able to, you will not get a good grade. If you do not do your homework as soon as you should, you will not get a good grade. Last time, if you don't do your homework as soon as you should, you're not going to get a good grade. I'm not going to say that you're going to fail, because you may skeet by with a 2.1, but you might have been looking for a 3.1. So don't just say, ah, God, I've got 20 days, I'll wait till Sunday the 6th, because you will not get this stuff done. And you are not going, well, you can try. You are not going to send me a nice email saying, oops, sorry, can I get an extension? Because the answer will be, can you remember on the 17th of November that Mr. Robertson went and said, if you don't do your homework when you should, your grades won't be as good as it could be, right? So that's up to you now. I think I've said that enough to be really boring. So let's focus on just one thing at a time. Let's get started on this topic called applications. There we are. I'm just getting used to the new locations. This is what we're going to cover. We're going to look at how do you find the center of mass of a 1D situation, one-dimensional. How you find the center of mass in a 2-dimensional situation. Neither of these actually use integration. Number 3 does. Find the center of mass, and I'm calling it the area of a function or functions. And then the last one is hydrostatic pressure, which, if you want to think about it, is just water pressure. So we're going to calculate how do you find what the total hydrostatic pressure on a plate that's been lowered down into the water. So if any of you have been as submariners, that's what saved your life, the fact that they were able to calculate what these hydrostatic pressures are. And I'm assuming they designed everything to support that. Okay. This is how you get the center of mass in a one-dimensional situation. You imagine that you've got a piece of wood that's infinitely thin, so it doesn't weigh anything. And in this particular case, you've got a mass M1 at position X1, another second one, we're calling it mass M2 at position X2, and one M3, right, mass 3 in position X3. So over here, I'll put some numbers on that as an example of how that might work. So imagine that I have, at this position here, I have an object that weighs 5 kilograms. At this position here, I have one that weighs 10 kilograms. And at this position here, I have one that weighs 4 kilograms. Now, when you're calculating what's called the center of mass, you're trying to find one point from somewhere between here and here, where if I put my finger on it, if I put a little fulcrum, right, a little balance point, it would balance. Now, it doesn't need to be over any one of these. In fact, the more likely it's probably going to be, I don't know, about here, right about there is a guess. But that balance point is called the center of mass. And you calculate it, well, you get a couple of things that when you put them together, calculate it. And the first thing is called little m, and it's basically the mass of the three things added together. So in this case, little m would be 5, 10, and 4. Which I believe is 19. And then you get a thing called the moment, capital M. And the moment is the mass of the object times its position. So in this case, mass 1 is 5 times -3, 10 times 2, and 4 times 5. And in this case, then, the moment, that's what we call this guy, the moment. The moment is whatever, -15, add 20, add 20. And I believe that comes out to be 25. So far, so good? So what is the center of mass? The center of mass, we use that. It's like the average x position. And it's the moment over the total mass. It's basically m1x1 plus m2x2 plus m3x3. That's the thing we call the moment over the total mass, which is m1, m2, m3. In this case, 25 is the moment and 19 is the mass. And the answer is 25/19. 25 divided by 19. And the answer is about, whoops, it's about 1.3. So somewhere around about here. And if you look at it, again, that doesn't seem that unreasonable. Do you agree? Seems so. What would that? Why would that be useful? Can you imagine that this is something that you want to support, right? So it's a steel girder, and on this steel girder there's pillars, right? And over here the pillar weighs 5 tons, and here it's a big long pillar and it weighs 10, and over here it's 4. So it's part of a bridge. Wouldn't it be helpful to know where was the best place to put a support girder? You see, it would go there. And what that would have the advantage of is, although those three weights are pushing down like this, aren't they going to be compensated exactly by putting you one girder at the balance point? For instance, see if I put the girder here, wouldn't there be a tendency for the thing to want to lean over? Because it's not well supported. So knowing where the center of mass in construction is very important. Have you ever noticed that bridges are almost always symmetric in at least one, if not two dimensions? Aren't they? When you see a bridge, isn't it, cantilever bridge, isn't it very symmetric? When you look at it this way, it's symmetric. If you look at it going down the road, isn't it perfectly symmetric as well? Well, not only is that aesthetically nice, right? Bridges would look funny if they were big and not quite big, but they try and do that if the terrain allows. Sometimes the bridge is going from a high point to a low point, and you can't do that. But it isn't just aesthetic. It's because these values of where to put support girders kind of make the thing symmetric. Because you're going to put it in certain places that are like in the middle of things. And when you put things in the middle of things, don't they just look symmetric? And so you can imagine that that's an important thing to be able to calculate. So with the center of mass in one dimension, we're looking good. Right, so I am going to give you one to try. So here is your infinitely thin guy. And we are going to have 4 guys on this. This one here is 5. This one here is 4. This one here is 3. And this one here is 15. Okay, find the center of mass of that guy. No pressure, you've got a minute.
You want us to tell you?
Oh, you're all right. You're ahead of the game. Okay, I'll just put down the key pieces. What's the top number at the moment? So if someone wants to check that they did it right, they agree with you. So what's the top one?
It'd be 4, or if you reduce.
Say again?
4.
Is that the full answer? But what's capital M? Because I don't think that's 4. That may be 4 here. Well, I'm not sure. You think that's 4?
I believe so. It's because negatives and then.
Oh God, yes, there's negatives and positives. What am I talking about? You're right. What about the mass?
It's 28.
Are you sure? I make 27.
I got 27.
Okay. So 4 out of 27 is the right answer, just because it's hard to imagine where that is. 4 out of 27. Yeah, it's easy done. 1.5, roughly. Right. So where would 0.15? It would be probably about there.
Professor.
Yes.
So the moment, so that,
Okay. Matthew? Right, you disappeared on me, so if you said anything after that, I didn't catch it. I think we're having technical difficulties, Matthew. You've probably... Oh, Matthew, did you finish your question? Because I didn't hear it.
I can say it again.
Yes,
so
please.
the moment, that's basically the total momentum.
Yeah.
So I guess I'm kind of having a hard time like understanding. So like, are the points moving or something? Like,
No, it's just the name they give to it. I think the fact you're calling it momentum might be the problem. Just pretend that there's another word called moment that sounds like momentum but isn't. These objects are fixed. They're fixed weight and fixed location. Nothing moves.
Is it okay? But is it like momentum from gravity or something like that? Or,
I think there's a thing in physics called M1V1 that you might be mistaking it for.
oh, that's what I was thinking it was.
Yeah, it's just coincidence of similarities in names, not
So-
really anything to do with each other.
is it like something though?
Yeah, it's like the force, it's like the turning force from, if you imagine 0 being the center, it's the turning force, right? The further away you are from the center and the heavier your mass, won't that turning force be strong? And if you're close to 0 and it's a small mass, then the turning force. And so basically you're trying to find the balance, because on one side, aren't you trying to turn it clockwise as far as 0 is concerned, right? at 0.
I think
At
it's
0.
also called torque, right?
Yeah, I was thinking that too. Maybe.
Right. Well, if we call it, if it's torque, will that make it easy in your brain to see what's happening?
I don't know. I'm just like confused because I'm thinking of like what I learned in physics and.
Oh,
they
I
interchange.
don't know.
Sorry.
Not with Jim. So you got, yeah. What you
I
saying?
think they
Sorry.
interchangeably use the words, so it can be confusing when they call it a moment.
Oh, right. I don't have that problem because I'm only going to call it a moment. And the poor engineers amongst you are now going to have to try and assimilate this knowledge into terms that you've heard somewhere before. And that makes your life a little bit harder than it does for us. For the non-engineers amongst us, of course, haven't we got an easier time of it? Because this is the only time you've seen this. I think as far as the formula goes, would you agree it's got a nice symmetry to it? Right? Mass times position, mass times position, mass times position, all divided by the total mass. And that works really well. Can we call that good then? That you know how to find the center of mass of a one-dimensional situation? Okay. So kick that out of the way. So how do you find the center of mass of a two-dimensional situation? Well, it's a little bit more complicated. I want you to imagine that this is it is essentially a flat piece of paper that's so thin it doesn't weigh anything. But at 3 locations, you have placed objects of mass M1, 2, and M3. And this guy has coordinates x1, y1. This guy has coordinates x2, y2. And this guy has coordinates x3, y3. And we are going to calculate what's called the center of mass. So at some point that I could place my finger on, the whole 3, you can imagine me doing it this way. Put my finger here, that would balance it, right? So people who work in circuses who have chairs balanced on top of sticks, balanced on top of bottles and all that kind of thing, they are using the fact that they know exactly where the center of mass is and they put everything vertically above it. And if you do that, it tends to be the most stablest position, right? So I'm going to stick to what they're calling moments in the textbook. And if you want to go and change them, I guess, to torque or something else, that's fine. So you need to know a couple of things to be able to calculate it. The first one's called the total mass, and we're going to use little m. And that's basically what you get when you add up the 3, which seems reasonable, right? Total mass. Then there are 2 moments. This is the moment my, and this is the moment mx. And yes, I know they look back to front. I cannot explain why they're called my and mx. But my actually does this calculation with x's, and mx does the same kind of calculation, but uses the y coordinates. Do you know what I mean when I say that these look like they should be called the other? But evidently they're not, and I'm blaming the engineers and the physics guys, because for some reason, that's how they look at these things, right? I believe it makes more sense when you go to 3 dimensions. And then this way of naming things makes more sense. But basically, the moment my is what you get when you multiply the masses with their x coordinates. The moment mx is what you get when you multiply the masses with the y coordinates. And the center of mass, which someplace roughly where my finger is, x bar, y bar. X bar is the moment y divided by the total mass, which is this calculation. And y bar is the same looking guy, but the y's. So if you take this guy out of the equation, doesn't that formula make sense? You see how the x bar uses all the x coordinate stuff and the y bar uses all that guy. Any questions? Are we good? Without getting into too much detail, because that will only confuse the calc students who are not into physics and engineering, is moments, or whatever you call them, is that something you've seen and done before in another world, in another class? All right, I get one nod I can see. There might be some other people nodding, but I can't see them. James, since you're the one I can see the view of, what did you do? Was it anything even vaguely like what I'm doing?
I don't know about 2 dimensions, but 1 dimension.
Right. And was 1 dimension just basically m1x1 plus m2x2 plus m3x3 over the
Yeah.
mass? Right. They never used the word moment. They used torque, or they didn't use any word.
They used both, I believe.
Okay.
They made sure they explained why he was using moment.
Okay. But you haven't seen 2D, or you don't recollect doing it in 2D.
I don't recollect.
Right. When you see 2D, do you see it has a kind of look to it that makes sense? Can you imagine if it was 3-dimensional, you just have a guy called Z bar, right? And it would be M1 Z1 and M2 Z2 and so on, right? Okay. So let's make one up. So we will have a guy down here whose coordinates are -2, -1, and he will weigh 5. We'll have a guy over here, he's going to be 10, and his coordinates are going to be 3, 2. And we can have one over here, and he's going to be 4, and he's going to be coordinates, oops, +1, -1. Okay, so we want to find the center of mass. Now, you don't need to do this, but I'm a visual person, so if you imagine joining these 3 points together, you make a triangle. Can you imagine at the ends of these triangles, there are weights of different amounts? So in this corner, it's a 5, here it was a 4, and away over there, it's a 10, right? In this situation, can you imagine that the center of mass is going to probably push towards this point because it's the heaviest, right? Does that make sense? So if I'm looking at where do I think the center of mass of this shape is going to be, my gut feeling is it's probably going to be about here. So you can kind of sort of visualize where the center of mass is. Well, its mass is what you get when you add those 3 guys together. So I guess I should call them M1, M2, M3, they're just labels. So what we got, 5 add 4 add 10, 19 again. The guy, the moment Y, is basically made up of all the x's multiplied together, those guys. So that's going to be 5 times its x coordinate plus 4 times its x coordinate plus 10 times its x coordinate. And that's what, -10, 24, I believe. And the moment of x's is m1, y1, m2, y2, m3, y3. And that's going to be the mass times the y coordinate plus the mass times the y coordinate plus the mass times the y coordinate. And I believe I get out of that 1. So x bar is going to be 24 out of 19, and y bar is going to be 1 out of 19. And just so I can roughly guess where that is, 24 divided by 19, oops, clear. 24 divided by 19 is about 1.3, and 1 divided by 19 is about 0.05. And I went and said somewhere about there, didn't I? Remember me vaguely pointing my finger?
Professor, someone in the chat saying you did something wrong.
Oh, what did I do wrong? Let's find out. Does anybody else know what I screwed up?
It's supposed to be 11, not 1, MX.
Yeah, thank you.
So we're
So let's
supposed,
put. So I'll make that 0.6. Is anything else wrong?
No.
Oh, good.
just
Okay,
have
so
a question in general. So
yes.
we're just supposed to give the approximation instead of the exact answer.
Well, no, we're meant to get the exact answer, and you finish with that. I'm
Okay.
just doing that so I can figure out where that is, because 24
Oh, yeah,
19s
yeah.
is not that obvious in my brain where that is. So it's about 1.3. So that's 1, 1, 0. It's about there, roughly, which is pretty good, because I'm cheating a little bit, but wasn't that where my finger was?
Yeah.
Right. So if you have an object that you wanted to find the center of mass, it is really, truly, isn't this nothing to do with calculus? Isn't this pure plug and chug, right? You just have weird formula that you can use, and as long as you know how to add, which evidently I don't, but if you do know how to add, you'll be able to do it.
Professor,
Yes, Matthew.
how come with the formulas for calculating momentum, how come it's like the opposite?
It's not momentum.
Or,
Don't use that word.
sorry, moment.
Okay, keep going.
How come it's like the opposite coordinates?
I have no idea. It ain't my fault. I only does what I'm told. And if physics people want to call them M bananas, I'm going to write down they're called M bananas, and you're going to ask me, why do they call it that? And I'm going to go, I don't know why they call it that. They've evidently got a good reason. I just don't care, because I'm not an engineer, right?
Okay.
And I'm not picking on you, Matthew. I'm just getting my gripe. The engineers, what's the word I'm looking for? They're like a species of their own. The way their brain works is so cool, but so different from the way my brain works. So, since I'm picking on engineers, how do you know an extrovert engineer?
He looks at your feet.
When he's talking to you. No? Okay.
That was
That's-
good.
Let you think about that one. I don't want to rush things if I shouldn't. But are we comfortable with this calculation now that you've only seen one? That there's not really much they're going to do except change numbers, right? The process is not going to alter. So where does calculus come in? Well, we've done center of mass of 1. We've done center of mass of 2. Now we're going to do the center of mass of the area under a curve. And I guess the good news is there isn't an M in sight. But there are quite a lot of integrals going on. So what do we mean when we ask you to find the center of mass for the area under a curve, area under a function? Can you imagine y equals f of x from A to B? There's the area. Now, what I would like to know is the center of mass, right? What point would be the balance point? You imagine that was made out of a piece of metal, right? And same density. And I was going to be one of those, those people in circuses that balance weird things, right? Don't you have to know where to put your finger to balance this shape? My guesstimate would be kind of somewhere about there. Would that seem reasonable? Ish. But we want to know the X and Y coordinate of that. It's called X bar, Y bar. And that if you go and look up the textbook, you can get proof of it. But essentially, it's a formula. The X coordinate of the center of mass, X bar, is 1 over A of this integral. And Y bar is 1 over A times this integral. And A is the area under the curve. And you can, as I say, you can go and look at the proof and find out why that comes out, but that's how we do it. So it's kind of plug and chug, but isn't it integration plug and chug? So you've got formulas that you're going to have to integrate, right? And when you're finished, it's going to be 3, 2, right? It's going to be two numbers, right? One is the X bar, the X coordinate of the center of mass, and the other is going to be Y bar. So let's get the show on the road. I'm going to pick the easiest function I can think of, which is x squared. And I'm going to start at 1. And I'm going to finish at 3. And so the shape that we're going to find the center of mass is that guy. Are we comfortable about, we know what we're trying to find the center of mass of, right? It's a plate of metal that would be this shape. Now, if I tell you that this guy here is 1 and that this guy here is 9, what coordinate, and this is a guessing game, and you are going to get it wrong, and that's okay. I am going to guess that the answer is at 2, 5. So I'm guessing about there. Anybody else want to have a guess? So we can all laugh at you when you see how bad you were. Emma, give me a guess.
I don't know.
That's what guesses are.
Put it 2, 5, but a plus or minus 6 on each.
No, you're not allowed to do that. I'm giving you a 2, so you're stuck with a 2. Give me another number that can't be 5.
-3.
You think it's going to be down here?
I don't know. You said guess.
Yeah, that is a guess, but I mean, shouldn't the guess
3.
at least be in the shape? Right?
2.5.
Okay. Anybody else want one more guess that doesn't have a 2 in it? And remember, it's got to be in the shape, right? That's kind of obvious.
0, 1.
Does that look like it's in the shape? Let's try
I
that
meant
again.
1, 0.
Okay. You think it could be there? Okay, let's figure out how to calculate this. First thing you're going to have to do is get A, this fellow. So it's going to be the integral from 1 to 3 of our function dx. So it's going to be 1/3 x cubed from x equals 1 to x equals 3. That's 1/3 3 cubed, take away a third. That's 27, take away 1, so it's 26 thirds. Okay, I can live with that. X bar is 1 over A. Are you happy about 1 over A becoming 326?
Yes.
Okay. The integral from 1 to 3 of x times f of x dx. So that becomes 3 over 26, the integral from 1 to 3 of x cubed dx. And that becomes 1/4 x to the 4, evaluated at 1 and evaluated at 3. If you plug in 3, you get 81 quarters. Take 3, 9, 81 quarters. Take away 1 quarter. 80 quarters, you get 20. If you do a little bit of simplification, divide top and bottom by 2, you get 30 on the top 13ths, which is round about 20 divided by 13. And so, try that again. It's about 2.3 roughly. So if that is 2, yeah, okay, that could be a 2.3. Now that's X bar. If you want to get Y bar, it's 1 over A, which is 326, the integral from 1 to 3 of a half f of x squared. So that's going to be 326, the integral from 1 to 3 of 1/2 x to the 4. It's going to be 3 over 26. Add 1 to the power, divide by the new power. Okay, you're going to go 243, take away 1 is 242 tenths. If you divide top and bottom by 2, you get 121, 363 over 130. 363 divided by 130. And that's about 2.8, which is definitely not there. It's much more likely to be a little bit lower than that. Assuming that I did these calculations in my head correctly. Has somebody got a change? Is there anybody in chat? Because I can't see chat. No, we'll assume that I did it right. The process is right, even if the counting isn't, right? So we now have a formula for calculating the center of mass of any object that you could possibly want, as long as you know its function. Yes.
Question. So, how it was in examples 1 and 2, like they were actual physical shapes. Like this example in 3, where it's a function that resembles the actual shape of it, right? It's not like
we are finding the center of mass of this shaded shape.
Like that's what the shape will actually look like.
Yeah.
Okay. Got it.
So when we talk about the center of mass of a function, we're really talking about the center of mass of the area under the curve of that function, which is what that shaded part represents. Now I don't have enough time to do the next one, but I can set it up because tomorrow we'll finish these off. But suppose I extend the question to one last situation. Suppose I have a function called y equals f of x, and we've got another function called y equals g of x. And at this point here, that's A, and at this point here, that's B. And the shape that we're trying to find the center of mass now is the area between two curves, right? These formulas have to be adapted to take account of the new situation. So when it was a single curve and the area under that single curve, did an A represent the area, right? This is going to be the integral from A to B. How will it change now that we've got this shape?
Fx minus g of x.
Correct. Does that make sense? That the area of the shape is the difference between the first curve, top, takeaway, bottom.
Damn it.
Now this guy is going to be 1 over a, the integral from a to b, and this one's going to be 1 over a, the integral from a to b. This is x, it's still x, and this is a half, and this is still a half, right? How do you think we adapt x bar?
Is that still going to be fx minus g of x? Man, this sucks.
We good? Now there's one last guy to adapt. This guy. Because there are two possibilities. One of the possibilities might be you subtract first and then you square. And the second possibility is that one. They are not the same thing. But only one of them is the correct thing.
Can you move it up just a little bit, please?
Right? One of them is the correct version that goes here.
Top one?
Because it follows this pattern. Any takers for the second one?
I don't think so.
Okay, then that's your problem to find out before I tell you tomorrow. Because if I tell you, it won't stick. But if you had to find out, it might stick a little bit more. Okay, that is, oh, almost forgot. Two things. First one is, make sure you say hi, get attendance. And the second one is, I sent out a report for everybody. Did you get that report? If someone didn't get that report, could you hold off for a few seconds and we can maybe figure out why the heck it's still not arriving? So that's it. Bye-bye, guys. So I guess there's a third possibility. Yeah. Okay. If it didn't arrive, send me an email saying it didn't arrive and I will just reply to that email. So that's you lot. So anybody with questions, you can hang about to the end. That seems more appropriate use of your time. Right. Bye-bye, guys. We learned some cool things today. Emma, you hanging about for a question? Ian, looks like you might be. Don't know. Ripken's gone. No, Emma's still here. Trenton, you got a question?
Yeah.
Okay, Ripken, are you here? Question? Don't know about Ripken. And Emma, you got a question?
Yeah.
Okay. Who wants to go first?
I guess I'll go first.
Okay.
It's question 5 from the test.
Okay. Could you tell me what it was?
Let me go get my piece of paper.
Okay. Is yours going to be about the test as well, Emma, or is you got a homework question?
It's about the test.
Okay. Oops. You back, Trenton?
Yep.
Okay, what does it
Okay.
look like?
It's y equals the ln of 1 minus x squared, and it's 0 is less than or equal to x, which is less than or equal to 1/5.
And what were you asked to do to this arc length?
Yeah.
Okay, let's have a look at that one. Basic, advanced. Right. Okay. So the arc length is going to be the integral from 0 to 1/5. Something wobbly. The square root of 1 plus the derivative squared dx. Okay, I'll do a bit at the side here. That's that guy. If you find his derivative, it's a chain rule. So it's 1 over 1 minus x squared times the derivative of 1 minus x squared. So it looks like this guy. When you square it, you square the top, you get this fella, and you square the bottom. You get that fella. So far, so good?
Yep.
Right, I guess I'll switch places because this will take more run than I've given myself. So you want to find 1 plus the derivative squared because that's what's going to go in here. And so it's going to be 1 plus 4x squared over 1 minus x squared squared. So I need to combine these to a single fraction. So I'm going to call the 1 that guy, and I'm going to leave that guy alone. You can then combine these, and while I'm at it, I'll FOIL this out. Combining those guys and rewriting it in a slightly different order from biggest to smallest. We get that? We good?
Yep.
Now, do you recognize that that top guy is a perfect square?
Mm-hmm.
And so you get x squared plus 1 all squared. Right. So over here, the arc length is the integral from 0 to 1/5, the square root of this fella. Which is what? X squared plus 1 squared over 1 minus x squared squared. Well, square roots play really well with squares. And we get to there. Things looking good?
Yep. This is
So-
exactly what I did so far.
Okay, so it must be the next stage. X squared plus 1 over 1 minus x squared. I need to make that guy by long division first. Why? Because it's the same power. So I'm going to do 1 minus x squared into x squared plus 1, which means -1 does the job. And -1 times that guy gets you x squared and -1, and then you subtract, and so you're left with this. That means that this guy is equal to -1 plus 2 over 1 minus x squared. Did you do that bit right?
I didn't long divide.
That's probably where it went wrong. But what we need to do after that is recognize that it's that,
And partial fractions.
and partial fraction it, and then and you got the answer.
All right. At least I was kind of close.
Well, I mean, you did. You got to there, didn't you?
Yeah.
Well, so you were given partial credit. You get about half the points. You get 5 out of 10, I'm sure. Right, Emma, you got a question now. We'll do yours.
Okay. It's the integral from 0 to -1. Okay.
Are you sure that's the right way? Because it should be negative
I
first.
said it wrong.
Okay.
Yeah. Then 18, and then e to the 1 over x divided by x cubed. But the 18 is not divided by the x cubed. I don't know. It was written weirdly. That messes me up every time.
I don't know where you put the 18 then.
But it's fine there. I put
It's
it
fine there.
outside the integral. is my-
Oh, that's fine. I would do that as well. In this question has a problem at 0, doesn't it?
Yeah.
Okay.
And so that was the main point.
So this question is going to be it diverges. So I have to prove to you that it diverges, right?
Yeah.
Okay. Now, the problem is not at infinity, isn't the problem at 0?
Yeah.
Okay. So what we're trying to figure out here is, what does this horrible thing look like, right? As x tends to 0.
Mhm.
So I'm just going to try and see if we can figure out how it would. Oh, the answer, by the way, is going to be infinity. I just need to prove it to you. Right. Do you remember a guy called L'Hopital?
Kind of.
Right. Okay. Oops. I will have to take a few seconds break. My dog is telling me it's poo walk time, and if I don't, she'll just bark all the time. So hold that thought. Come on then, let's go. Okay, I'm back. She wants to go out, and then when she sees it's miserable, she doesn't want to go out anymore. So she's kind of weird that way. Now, all I need to do is prove to you that this diverges. So that's the way I was originally going to do it isn't going to work, because I'm just trying to find this thing. I was trying to prove it's infinite, but that's not actually a good. It's not a good proof, because if I do L'Hopital in that, forget the 18. What you get is e to the 1 over x times the derivative of that, which is this fella. And then you get 3x squared. So all you end up with is and if I keep doing it, it just gets bigger and bigger and bigger and bigger. So that isn't particularly helpful. It's a bit of a fudge here, but here goes. If I brute force this, would you agree it's 1 over 0 and 1 over 0 is infinity? And so we have e to the infinity. And if I go 0 cubed here, I get 0 cubed here, which is basically just 0, right?
Mhm.
Now, what happens if you take a number, you take something, like infinity, and you divide it by 0? Don't you get an infinitely big answer?
Mhm.
And so I'm just saying that this function is infinite as you get to 0. And I'm saying that it diverges because it gets to infinity really quickly. That's not a very good explanation, because the only one that I could have done would have been a question that looked like this. Because then I could have proved to you by doing a U sub.
Okay, that's where I went with this.
Right, now the U sub has, it is possible for me to do a U sub. I think, let me try it. Oh, forget about the 18. Stick it out there like you did. Now, if I use this fella here as my U sub, then du by dx ends up being negative 1 over x squared, which makes the crossover
Mhm.
that guy. So we will get the integral from negative 1 to 0, and e to the u,
Mhm.
an x cubed, and a negative x squared du, and that gets me the integral from negative 1 to 0, e to the u over x du,
Mhm.
which gets me
You said-
that fella.
Yeah.
Now, that 0 should be called t. Okay, the hard part is over, believe it or not. Won't I be able to integrate this using integration by parts?
Okay.
Right? Now, if I call this f and I call this g, we're going to get the limit as t tends to infinity of f dash, I guess it's u, g of u, take away the integral, oops, capital G of u. I'm not going far too quick for my own good. There we go. We'll just do that with all these fellas going on. So what do we get? We get u e to the u, take away the integral of 1 times e to the u. So you get u e to the u, take away e to the u, which is e to the u take away 1, which is e to the 1 over x. 1 over x take away 1. Great.
Mhm.
Evaluated at x equals negative 1 and what x equals t. So what do we get? E to the 1 over t, 1 over t take away 1. Take away e to the negative 1 with a negative 2 in it. Okay, brute force. E to the power of 1 over 0, 1 over 0 take away 1, plus basically that guy. Okay.
Mhm.
1 over 0 is infinity, right? Infinity take away 1 is infinite. 1 over 0 is infinity, E infinity is infinity, can you see that the answer is infinite, so it diverges?
Okay.
You went the right road, and I can see why you might have either stopped or not. I can't remember what you wrote, or didn't continue. Was it that X that was left over just to throw you?
No, I got to, you know, that line right there.
Right.
And then I thought to do integration by parts, but then I didn't. I don't know why.
You just
I
talked
was-
yourself out of it, right?
Yeah, I was really confused, and the book has a very similar problem, and its answer was 2/e. And then I was just like, you know, that's it.
Okay. Well.
So that was really confusing.
Oh shoot. The answer is 2/e. The answer is 2/e. I forgot something. Isn't u 1/x?
Yes.
So can we get to here and pretend I never did the next bit? It's e to the 1/x. 1/x take away 1, right?
Mhm,
And it's going to be the integral from -1 to t, right?
mhm.
So it's going to be evaluated at x equals -1 to x equals t. And that's going to be the limit as t tends to 0. That's better. So it's going to be 1/t, 1/t, take away 1, subtract e to the -1 times -2. So that's where the 2/e comes from this piece. And this fella here is going to be, that diverges. Yeah, it still diverges. Yeah, when I saw the 2/e, I understand where you got it from. I was fine. Because 1/0, 1/0 minus 1, that's a whole load of infinities, and that's why it diverges.
Okay.
I don't know why the other one is similar. Maybe it had x squared in the bottom instead of x cubed. Maybe that's all it took,
That's probably it. Yeah.
right? I mean, that all you need to do, or you could change the 1/x to 1/x squared, and you might get a similar result. You know, it's the same kind of thing. Like that diverges, but that converges. You know, just an extra x will change the answer. Okay.
Okay. Bye.
Do you mind if I keep this part of the video, or do you not want me to?
I don't
Nope.
care if I look dumb.
Yeah, oh God, you do not look dumb. Don't even think about that. I make enough mistakes for everybody, so you're totally safe.
Okay. Thank you.
Okay, you're welcome. Right, bye bye then.